Welcome everyone to this webinar on how to successfully adopt additive manufacturing in the workplace. I'm Steve Taylor. I'm a technical trainer here at 3DGBIRE, and alongside me I've got Jordan Allen, our marketing executive, who will be looking at some of the case studies later on as we move through the presentations. So, why have we decided to run this webinar? What we found is one of the barriers we have found in organizations with successfully adopting additive manufacturing is that for successful adoption, there has to be a number of skills that are within an organization. And we've actually narrowed it down to 7 skills. So in this webinar, what we're going to do, we're going to look briefly at each of these 7 skills that we see are the tools or the skills that are required within an organization for that successful adoption. We'll also provide you with an overview of the range of technologies available for additive manufacturing, and then we'll look at a couple of applications and case studies where additive manufacturing has been successfully adopted in the workplace by organizations. I hope that this, by the end of the webinar, will have addressed most of your concerns and that you'll feel confident in what steps you need to take in your additive manufacturing journey afterwards. So let's move on to the next one. As with the many disruptive technologies, the sector growth has happened much more quickly than the pace of learning for the workforce. There are many reasons for this lag, but one major culprit is a skills gap. Additive manufacturing is so different from traditional manufacturing that many workers simply don't have the right skills or can't be trained fast enough to upskill into these new roles. To better address the unique skills that additive manufacturing requires, you must first understand that it's not any single technology, but a whole integrated set of manufacturing technologies and processes. Therefore, a highly trained additive manufacturing workforce will be needed to be skilled in the following multidisciplinary roles. So if we look at them, we've got the knowledge of additive manufacturing. So what type of machines are out there? What sort of manufacturing technologies are available for the applications? There are computer-aided design skills. We've got design thinking. Some people refer to this as design for additive manufacturing, or DFAM. We've got material science. There's been a massive increase over the last couple of years in the range and types of higher advanced engineering types of materials that are now available for printing with. You've got the post-processing of your prints. So what do we do after we've 3D printed it to make it into a usable part? We've also then got reverse engineering. And then finally, one of the major things as well is the critical thinking and soft skills that are required. So what do each of these skills comprise of? Well, if we're looking at the knowledge of additive manufacturing, what we've got material extrusion. It's commonly referred to as FDM or FFF. This is the process that most people are familiar with. We've also got vat polymerization, which is the first type of 3D modeling as we know it today. We've also got direct energy deposition. Then on the other side of the circle there, we've got material jetting. We've got binder jetting, sheet lamination, and powder bed fusion. We look at more depth in vat polymerization DD on separate webinars, but for anyone new to additive manufacturing, then I would always start with FDM or FFF. So before we even start looking at any of the machines and the technology, one of the things that we need to know or understand is how we get a model ready for being able to be placed onto a 3D printer. And one of the first things that we need is an electronics file design of the actual part that we want to recreate. So if you look at the picture on the left-hand side, what we've got an Apple model that has actually been divided up into what we call slices. Now, this is done in a specific slicing software. Now, there's a number of different ones on the market, but eventually they all really do the same thing, which is dividing up the 3D part model into subsequent layers, which when placed together will create a complete model. Now for FDM, the type of layers or the coding that comes out of the machine is a G code. Now what the G code does, that actually moves around the printer head in a predetermined path to be able to lay or deposit material in a pattern to complete each one of the layers. And then the build plate will then lower down, and then it will then follow another path to lay material on the previously laid layers. A second type of slicing output are images. Now these images are full bed images or build plate images of each layer, and these are usually used for like SLA types of machines or DLP type machines, where a light is projected or a laser is projected on a full bed. The layer or image that is projected is then projected through a resin material. The material will actually harden wherever the light passes through it, and the initial layer will adhere to the build plate. The build plate will then either raise up or raise down, depending on the technology being used, to the next layer height, and then the next layer is then projected through the resin and cures onto the previously laid layer. So that's really what happens. Your model gets sliced up into layers, and depending on the technology, the coding or the images are produced by the slicer for then being able to be placed onto the 3D printer. Here's just a quick video. What we've got, fused deposition modeling or fused filament fabrication, FFF, is an additive manufacturing process that belongs to the material extrusion family. In FDM, an object is built by selectively depositing melted material in a predetermined path, layer by layer. The materials used are thermoplastic polymers, and they come in a filament form. FDM is the most widely used 3D printing technology. It represents the largest installed base of 3D printers globally and is often the first technology people are exposed to. A designer should keep in mind the capabilities and limitations of the technology when fabricating a part with FDM, as this helps to achieve the best results. As I mentioned earlier, FDM is always the technology we would promote for someone new to additive manufacturing. There are lots of different manufacturing machines out there, and each manufacturer has their own unique machines with unique selling properties and manufacturing properties. We've got Ultimaker. So looking at some of the machines that we sell, we've got the Ultimaker range. Now we've got 3 models that we're currently selling. So we've got the Ultimaker S5 Pro bundle, the Ultimaker S3, which is slightly smaller, and the Ultimaker 2 Plus Connect. Now we can obviously split the bundle up, the Ultimaker S5, and it's just the Ultimaker S5 print machine. What they have really is this is an FDM machine. Use dual deposition, so you've got 2 nozzles that will deposit either a single build material, a build material with a support material, or actually a dual build material. So you can actually mix and match different materials for one print. The thing with the Ultimaker range as well, they've got a massive, large marketplace with lots of different plugins and materials available that seamlessly merge into the Ultimaker ecosystem. You can also manage your printers remotely. Ultimaker have the Ultimaker Digital Factory. This allows for managing of multiple machines, for multiple user management, and also to be able to manage your print queues and your complete printing ecosystem. Another manufacturer that we have is Raise 3D. Now the Raise 3D, with the 3 models that we currently sell, we've got the Pro 2, the Pro 2 Plus, and the E2. As you can see there, we've got a lot of, these are larger volume print machines. The Each come with standard with a hood and a cover and a UFP carbon filter. They're highly recommended. Again, very much like the Ultimaker, they have their own material filament providers that they've got all the settings for the printer. And also you can manage your printers again remotely from the cloud. So you can monitor and streamline your operations. We also just recently have the BCN range of machines. Now, the BCNs come with IDEX, which is independent dual extruder. So this is again a unique selling point for this type of machine. What it does do, again, it's got two deposition nozzles, but it allows you to print either a single build using both nozzles, so a single build with support material, or if you want to up your printer speed, being able to not just make it into a one printer, but like act as though it's a two printer, what you're able to do is add the same material into both nozzles and print in either duplication mode or mirror mode. What this means is that both nozzles will move either simultaneously in the same direction or opposing directions to be able to create two models at once on your build plate. And the BCN has quite a large build plate volume as well. So if you look there, the Sigma D25, it's 420 by 300 by 200 high, up to the Epsilon W50 on the right hand side, which you're going from a 420 by 300 by 400 high print volume. So again, large volume and, you know, the IDEX system within this type of machine. Moving on now to a different type of skill, computer-aided design. Now, to me, computer-aided design, or referred to as CAD, is the backbone of additive manufacturing, since you use the output from the 3D modeling software to create or reproduce your geometric form. That's why CAD is one of the most critical skills in additive manufacturing. Designing, modifying, or improving an existing 3D model. The creativity and knowledge of a skilled CAD designer is not something that you can easily replicate. While CAD design software has become more accessible and user-friendly, anyone using it still needs to have a bit of knowledge of the way that parts go together. They've got to be skilled in things like design thinking, computational modeling, analysis, and obviously engineering. Because of the sheer number of different competencies involved, can often be the most difficult of the additive manufacturing skill sets for prospective operators to master. So if we move on again, looking at design for additive manufacturing, AM prints from CAD models by adding materials layer by layer. This process is the opposite approach from most traditional forms of manufacturing, which remove or subtract material to form the desired shape. Often with the desired shape modified for the machining available and potentially a non-optimized part produced. So your CNCs, with your CNC cutting, you'd start from a solid block, you'd then machine what you could with that tool, and potentially it might not be an optimum part, but it will do the job that it's designed for. If you want to optimize the part, you then have to start potentially turning the orientation of it, remachining it in 3 or 4 different setups, which is not adding any value. It is optimizing it, but the initial machine part would have done the job. So why spend all the extra money doing that? What additive manufacturing does, it frees designers from this type of mindset. The layer-based additive nature allows for high degrees of customization on complex geometries. These provide you with the flexibility to integrate features into complex parts without the simplification needed for most conventional subtractive production methods. This freedom and flexibility means that designers can think conceptually much differently when working in additive manufacturing, offering more of an opportunity to design from a a blank slate or a empty bed plate, you know, if we look at it from an additive manufacturing point of view. However, AM still has its own considerations, whether it is the material selection, support or build strategy, or choice of which process to use for a given project. The most important aspect of design for additive manufacturing is to identify and take full advantage of the tools available to get the most benefit from things like generative design, topology optimization, and the lattice structures which are now available within these softwares. Additive manufacturing has matured over the last decades and has become a constant in our product design and development cycles. We have a much wider range of materials and we can produce much stronger and more accurate components in a shorter amount of time. There is a whole material science now behind the choice of the correct material for the process and the end parts. And with the ever-increasing materials catalogue, which I spoke about earlier, including standard non-filled materials, your filled materials, and your engineering advanced materials like glass and carbon filled, and even now metal you can print with. Using the correct material for the application can save you time and money. Things to think about when selecting the right material are the properties. You know, what is the key features and functions of this particular part? What does it need to do? The processing parameters. So what temperatures are we going to be working at to be able to produce this part? The performance of the part. So are there any structural loads that are going to be applied to it in use? And obviously the common applications for that type of material and the part itself. So that's really just, again, delving into the material science side of things. But again, one of the bigger skills here is the post-processing of parts. Additive manufacturing is not only about designing and preparing your project for 3D printing. A distinguishing professional feature is the level of post-processing skills needed to make realistic and accurate model representations. So some of the things that you're going to be looking at, potentially depending on the materials you're working with, depending on the expected outcome of the part, is it going to be hidden away so you're not looking at aesthetics, or is it something that, you know, it needs to be smooth and shiny and you know, look as though it's been injection molded, you know, that sort of surface finish? You know, we need to look at things like support removal. We may need to do some grinding or sanding, maybe some cutting, filling in some areas, maybe painting, coating, or even polishing. So finishing is especially important when creating 3D printed production parts because they provide different challenges than conventional machine parts. The layered 3D printing process of some machines may not be as accurate as some traditional production methods. That's why you may still need to employ traditional CNC machines in the 3D finishing process. So maybe you're looking at, you've got an FDM machine and you want to make a drill jig, but your drill jig has to be a 10% tolerance of the original actual manufactured part, which means that potentially you've got to go down to 10 microns on your template. It could be that the additive manufacturing process will not be able to hit them finite tolerances for every hole. So what you do is you would fill in the holes with material, so make it a complete part, and then just put it on for a final either reaming out or a drilling and reaming out to get the desired accuracy, again, on a CNC machine. The technology is changing. It is advancing monthly, weekly, daily. So I can see it not being too long before actually them sorts of tolerances we are going to be able to get on, you know, some of your desktop machines that, you know, are a lot cheaper than your conventional CNC machines. Ultimately, the material and the technique chosen for finishing your 3D printed pieces depends on, you know, the application requirements. You know, is it a prototype? Is it a presentation model, or is it a functional part? It's essential to understand and master the various post-processing finishing methods available so that you can meet the desired outcomes of that part design. One of the big advantages that additive manufacturing does give us, though, is the ability to reverse engineer or look at reverse engineering the part, but not only just to recreate the part exactly as it was, but to potentially look at how can we make it better. You know, it's all right being able to replicate a part and reproduce it, but it gives us the opportunities to actually rethink and potentially redesign that part. Now, an attractive feature propelling the optimization for many companies is the prospect of utilizing 3D printing for the obsolete or replacement parts inventory. So there's a high degree of reverse engineering that may be required to both directly replicate legacy parts and incorporate any part improvements enabled by additive manufacturing. Tight tolerances and high resolution 3D laser scanners can capture these sometimes difficult geometries, requiring quality control and testing before production. And not every re-engineered part will be a good candidate for additive manufacturing. That's one thing that we need to, make clear. Additive manufacturing is not going to be able to replace everything straight away. Yeah, a well-versed designer is aware of the methods and limitations of additive manufacturing, as well as other manufacturing processes, and can choose the most appropriate solution, or even, as we mentioned before, a hybrid solution where you'll potentially print a near net shape in your additive manufacturing material and then just incorporate a CNC cutting head or smoothing head afterwards, just to get those intricate features or faces or potential tolerances that you need on these key sections of your part. And then finally, the final skill that we see as required is critical thinking and soft skills. So while there's always a focus on hands-on technical skills, the overall level of critical thinking and problem solving involved in the entire manufacturing process should not be overlooked. Likewise, the value of interpersonal skills such as communication, collaboration, and leadership abilities are equally important factors for your additive manufacturing workforce of today and tomorrow. Your workers are the best advocates for additive manufacturing, but they need to be able to articulate its value to senior management to encourage its broader use and adoption in creative ways. My personal view is that additive manufacturing is poised to have a dramatic impact on manufacturing, but it's still in a relatively early stage and has yet to reach its full potential or complete industrial adoption. One of the significant hurdles it's facing is a qualified workforce to run it all, which is why this level of expertise is in high demand. So whether you're an additive manufacturing professional seeking advanced opportunities or a business leader seeking new talent to help you take advantage of the technical advancements additive manufacturing offers, you need to cultivate these skills for your workforce of the future. So it's a really key sort of skill that we need to look at. So that's really the 7 skills that we see that the companies need to adopt to be successful in additive manufacturing. Now I'm going to hand you over to my colleague, Jordan, who will look at some case studies with.
Thanks for that, Steve. Yeah, that's right. We're going to dive now into a few different case study examples that we've developed here at 3DGBIRE. The first one is going to be JG Plastics, and the second is going to be Team Dynamics Motorsport team. Okay, so let's start with JG Plastics. So first of all, we're going to meet Graham here at JG Plastics. He's based up in Bury, Manchester area, so not too far from us here at 3DGBIRE. Now Graham is an experienced CAD designer. He's had plenty of experience over the years designing different parts, However, he was getting them fabricated, he was paying to have them fabricated and outsourcing that work, which was costing him quite a significant amount of money, and it was obviously taking away from his profit at the end when he came to sell the end-use parts. In this particular case, we managed to dig into a couple of parts that Graham was previously having machined as metal parts, and he managed to CAD those designs up and start printing them as plastic PLA parts on his raised machine. Now typically Graham was producing these parts at £1.50 per unit, which is obviously quite an expensive cost price. He managed to reduce that down to just 25 pence per cost price, obviously saving there £1.25. Now the real cost saving came in how many of these that Graham produces. He produces 20,000 parts every 10 weeks, which works out about £2,500 a week. Obviously the ROI in that investment, I think a raised machine would probably be covered in, well, more than covered in just 2 weeks. So a really fantastic example of how someone can quickly recover that ROI investment on a 3D printer, which may seem quite a significant initial cost. However, in this case, obviously Graham's recovered that quickly. He also discusses the time-saving benefits, how the labour cost of production is significantly reduced. He simply has to stop and start his machine at the end of each day and the start of each day. So yeah, a real good example here of how 3D printing can be applied to a traditional manufacturing business. And yeah, Graham's a very happy customer of ours and a really good story. So anyway, let's move on now to our next case study, which is Team Dynamics. So now let's head down to Team Dynamics. Team Dynamics are a British touring car championship team based in Birmingham. Team Dynamics are responsible for producing a number of high-end components for their car and various other cars within the championship. They've developed air intakes, bonnet louvers, fixtures, fittings within the car that obviously have to withstand high temperatures and race conditions. This is something that takes a series of prototypes usually, and in the past there's been a very expensive process to lay up prepreg composites and figure out how these parts are going to work. Testing and trialling these parts could be months and months of testing, receiving back a prototype, then readjusting the design and coming back again to retest. 3D printing has allowed them to change this process completely. They can now redesign parts overnight, print them off, and they can be ready to test again the next day. This has allowed them to develop a USP over the other race teams in that they can speed up their manufacturing and design process for the car, and also the production process, which has allowed them to sell on parts to other race teams and develop a whole new side to the business where they can generate revenue using the printer, selling on parts. And that's the big thing to take away from this presentation today, is that with the right knowledge and the right skills, anyone can use 3D printing to develop a USP for your business and to solve problems that previously might have been incredibly difficult. There's no one right solution for everybody. Everyone's problem is going to be different and everyone's solution is going to be different. But here at 3DGBIRE, what we want to do is guide you through the process. We want to help you understand the skills you're going to need to help get the most out of additive manufacturing for your business. And we hope that you've learned a lot today. There's still a long way to go on your journey, and I'm sure you feel like you're just getting started. So if you want to take the next step in 3D printing, get in touch with us today, and we can hopefully get one of our consultants to get in touch and get you started with the first few steps of the process. Come down to your business perhaps, find some applications, find the right solution for your problem, and take it from there. And thanks for joining us today, and thanks to Steve Taylor for a fantastic presentation earlier on, and we hope to speak to you soon. Thanks again, and goodbye.